Digital logic circuits can be divided into combinational logic, in which the output signals depend only on the current input signals, and sequential logic, in which the output depends both on current input and on past inputs. In other words, sequential logic is combinational logic with memory. Virtually all practical digital devices require sequential logic. Sequential logic can be divided into two types: synchronous logic and asynchronous logic. In synchronous logic circuits, an electronic oscillator generates a repetitive series of equally spaced pulses called the clock signal. The clock signal is applied to all the memory elements in the circuit, called flip-flops. The output of the flip-flops only changes when triggered by the edge of the clock pulse, so changes to the logic signals throughout the circuit all begin at the same time, at regular intervals synchronized by the clock. The output of all memory elements in a circuit is called the state of the circuit. The state of a synchronous circuit changes only on the clock pulse. The changes in signal require a certain amount of time to propagate through the combinational logic gates of the circuit. This is called propagation delay. The period of the clock signal is made long enough so the output of all the logic gates have time to settle to stable values before the next clock pulse. As long as this condition is met, synchronous circuits will operate stably, so they are easy to design. However, a disadvantage of synchronous circuits is that they can be slow. The maximum possible clock rate is determined by the logic path with the longest propagation delay, called the critical path. So logic paths that complete their operations quickly are idle most of the time. Another problem is that the widely distributed clock signal takes a lot of power, and must run whether the circuit is receiving inputs or not. In asynchronous circuits, there is no clock signal, and the state of the circuit changes as soon as the inputs change. Since asynchronous circuits don't have to wait for a clock pulse to begin processing inputs, they can be faster than synchronous circuits, and their speed is theoretically limited only by the propagation delays of the logic gates. However, asynchronous circuits are more difficult to design and subject to problems not found in synchronous circuits. This is because the resulting state of an asynchronous circuit can be sensitive to the relative arrival times of inputs at gates. If transitions on two inputs arrive at almost the same time, the circuit can go into the wrong state depending on slight differences in the propagation delays of the gates. This is called a race condition. In synchronous circuits this problem is less severe because race conditions can only occur due to inputs from outside the synchronous system, called asynchronous inputs. Although some fully asynchronous digital systems have been built, see below, today asynchronous circuits are typically used in a few critical parts of otherwise synchronous systems where speed is at a premium, such as signal processing circuits.